G'day everyone. Today's lesson we're going to look at primary standards. Primary standards are a really important aspect of the Year 12 course when it comes to titrations. We can't do a titration unless we have something to measure it against. So preparing a primary standard and knowing what it is and how it works is really important. Every year in the WACE exam there's some question related to the technique, either the preparation of the primary standard or actually what constitutes a primary standard. So let's have a look at that and we'll get into it. Okay, so what is a primary standard? Well, first of all, what's a standard? A standard is something against which something else is measured, and we have lots of standards in life. Some examples, or an example actually, is one for mass. Now, for a long time for mass, in France they had a 1 kilogram mass of a platinum alloy, and every other country had a copy of that, but there was one standard, and that's in the picture there. And everything else was copied against that. So that was the kilogram. So in the US there was a copy, in Australia we had a copy, in the UK they had a copy, and all around the world they had copies of that. So that was the secondary standard in each country, was the one that was compared to the primary standard. But over time, and there was one for the meter and a whole heap of other physical quantities as well. But sadly, because physical objects decay over time, and some radioisotope decays, they found that the mass of the platinum actually altered over time and got less. And in some cases you can actually have it increase because it might oxidize or something like that. Even though they kept it in a vacuum vessel, as you can see, a double bell jar there, they found that it did change. And you couldn't even touch it, for example, so the oil from fingers or even the air breathed onto it could change its mass. So they found that that wasn't that reliable. So in 2019 they changed it to something a lot less fun, I guess you could say, and you can see that they defined it by setting the Planck's constant h exactly to that number, and given the definitions of meter and second. So in other words, they define it to something to do with light and energy. So not as easily quantifiable in our brains, but something that could be used anyway. So in chemistry, a primary standard is a substance or a reagent. A reagent is something that's used in a chemical reaction that is very pure, is very much representative of the number of moles of the substance that it contains. So in other words, that relates to purity. So if it says it's 100 grams, it's 100 grams of that substance. Or moles, 1 mole is 1 mole, and it's easily weighed. So a reagent is a chemical used to cause a chemical reaction with another substance. Sometimes we call it a reactant, but we call it a reagent in a chemical reaction. So we use them to test for the quantity or the presence of specific substances in a solution. These are crucial in titrations as we have to have something to measure against. Now, characteristics. This is definitely a WACE question. This is something that comes up quite often. You look back through the last few years' WACE papers and you're going to see that primary standards, the characteristics of primary standards are always asked. And often students go to the easy ones or something that's just too general and they get it wrong. You've got to actually be quite specific when it comes to these characteristics. So the features that you need to remember is 1, and this is the most important one, they have to be available in high purity. They have to be stable and low reactivity. Often in the WACE exam it actually pays to say low reactivity with something like oxygen, or low reactivity with water, or low reactivity with CO2. So you're actually specifying what the reactivity is, but stable. Low hydroscopicity, which basically means that if there's lots of humidity in the air, it doesn't absorb the water from that. So a lot of substances do that, and that's what the number one reason really why you don't have everything as a primary standard. There's only a few, so that's a good one. So try and remember that one. Hydroscopicity. High equivalent weight. So the higher the molecular mass, the better, basically, because the higher your mass is, the less you're going to have weighing errors. There are a couple more which aren't as important. Non-toxicity is preferable, but it's certainly not a most important characteristic, so I'd steer away from that one. And readily available and cheap is another one. But again, I'd steer away from those last two because you really want to focus on what the chemical nature, the chemical properties that make it special. In terms of what is a primary standard, we're focusing on acid-base titration. So we really have two. You can't go wrong by quoting either of these ones. Anhydrous sodium carbonate, so that means with no waters of crystallization involved, and oxalic acid. Now, depending on what you're trying to standardize would depend on what you use. Although you can use both, it's just a little bit more complicated. If you have a base that you want to standardize, obviously you'd use oxalic acid. If you have an acid that you want to standardize, you'd use a sodium carbonate. Sometimes we have a series of standardization. So we do one with one of these substances, and then we do another couple later on with other substances. So we have a primary standard, secondary standard, tertiary standard, etc. Okay, so there are a number of ways in which you can prepare a primary standard. If you go to different universities or you look on different websites, you'll find slightly differing procedures. The way they do things at measure, for example, in certain places it differs, but in the essence we get the same overall result. Why do we need to do it? Again, just to reiterate this is quite important. Sodium hydroxide, for example, one of our most common bases, can't be used as a primary standard because it doesn't meet the criteria. So what we would do is we would prepare an oxalic acid solution as our primary standard solution and titrate that against the sodium hydroxide. The sodium hydroxide, we now know its concentration, so we call that the secondary standard. So, for example, you would have seen a demo in your class that looked at some ethanoic acid or some vinegar, and we were trying to find out what the concentration of the ethanoic acid was. And we used sodium hydroxide, and we said we knew the concentration of that precisely to figure it out. How did we know the concentration of the sodium hydroxide so precisely? We would have tested it against some oxalic acid, primary standard. So a primary standard is one of those two substances I mentioned, and you get a secondary standard from that. So how do we make it? Anhydrous sodium carbonate can be used as a primary standard. That's one of the most important ones. And remember the anhydrous bit. It doesn't have any water, and you can get it cheaply, and it comes in 99.9% purity, which is great. So we can use solid sodium carbonate, but we've got to get rid of that water first. So what we need to do is get rid of that last little bit of water that might be lingering around, and we do this by heating essentially. So we might weigh out, for example, 2 grams of solid sodium carbonate on a clean, dry watch glass. Now the mass doesn't really matter. The mass is all, it's about what's your final solution's concentration going to be. So you probably have to weigh out a bit more than what you'd need. So I'm going to give an example that uses 1.3 grams, but you'd weigh out a bit more. Put it onto a clean, dry watch glass. Put that watch glass into an oven at 100 degrees Celsius to make sure that you evaporate all the water off. Less than 270 because you don't want it to start to decompose. Remember, water boils at 100, so as long as the oven is just over 100, that will boil the water off, will evaporate the water off, which is all you need. So they usually use about 260 to make sure that happens. After 30 minutes, you take the watch glass out and you put it into a desiccator. A desiccator is like a special glass vessel that you have a chemical in the bottom that absorbs the water. So it's a substance that dries things. It's a device that dries things out and stops it getting any more water. Sometimes they even put them in a vacuum desiccator, which means they suck all the air out in total to make sure that there's no chance of that sodium carbonate grabbing back any water. Let it dry and cool, and then reweigh it. And you keep weighing it until you get constant weight. So you would weigh your 2 grams, dry it, let it cool, weigh it again. If it's 2 grams again, you're right, all the water's gone. But it might be 2 grams has gone down to 1.99. Then you heat it again, it goes to 1.98. Then it goes to 1.96. Then it goes to 1.95. And then you weigh it again, it's 1.95, 1.95. And when you get that consistent mass, you know you've got rid of all the water. If it ever goes up, the reason it's gone up is that it's absorbed some water somehow in the process. So this is the process how you make the solution. Now these differ a little bit from place to place, but this general procedure will get you over the line if you're ever asked questions about it. So first of all, we've got to prepare the solution by getting a volumetric flask. And indeed, any glassware that you're going to use for this process, you know, if you use a beaker or a glass rod or a glass funnel, whatever the equipment you're going to use, you have to clean it in the same way. So we put a little bit of distilled water into a clean, dry volumetric flask. We swirl the water around to the interior of the flask to rinse it. Throw the water away. If you see the water with a really thin layer around the flask, we can say it's clean. If it has any droplets in it, then it's dirty. So you need to wash it with detergent, then dry it again. So at university when we used to do these all the time, one thing I had to do was you do it 3 times. So soap, water, rinse, soap, water, rinse, soap, water, rinse, and then you dry it in like a pie oven sort of device to get all the water out. If you get any beading, so the water's little droplets, got to restart and do all over again. So you'll do this to your beakers, to your stirring rods and all the other pieces of equipment, as I said. Now, if we wanted to make a specific concentration of sodium carbonate solution, we weigh out a mass. We put it into a clean, dry watch glass, a rowing boat, or a small beaker. And we use the most accurate balance that we can find. So on the picture there, you can see that's the balance, and there's a boat, we call that. It's a little device to weigh things. Got to be working pretty quickly because the sodium carbonate will absorb that water, suck it out of the air really quickly. Next step is that we put a clean glass funnel like this into the neck of the volumetric flask and leave a little bit of an air gap so we don't get an airlock inside. Now this is where it differs depending on the procedure. There's a procedure on our OneNote that is a bit different, but this is the way that is recommended to do it. What you shouldn't do is add solid directly to a volumetric flask, because if it doesn't dissolve, you can't do anything about it. So what you do is you get a clean dry beaker, cleaned in the same way the volumetric flask was, and a stirring rod. Then what you do is you add a little distilled water and you swirl it until you can dissolve the solid, or use the stirring rod. Break it up with the stirring rod tip if you want. You might need to add a little bit more water, but what you'd never do is you never heat the beaker. There's a real temptation to heat it up to make it dissolve faster. But if you heat it up, you change the density of the water, and it's going to change the volume, so we don't do that. Just use it at room temperature. Then what we do is we take your weighing boat or your watch glass back to the balance and measure it again. So you would have measured out 1.300, for example, put the watch back on, and if there's any mass on that, then that's some residue left on the glass. So you take that away from your initial value, and that's the mass that you actually have. Another method to do that is, instead of re-weighing it, you take the watch glass and basically rinse it a lot into the beaker, trying to get every last bit off. But either method is valid. Rinse a stirring rod, so get your stirring rod and actually rinse it off with the water and put it aside. Then what we're going to do is get the solution into the volumetric flask, as you can see in this picture here. So using the funnel, transfer the solution to the volumetric flask, and as you do it, as he's doing in this picture, you can see here on the screen, you use the washing bottle to rinse out the beaker. And what you want to do is make sure every droplet of water goes into that funnel. So you rinse, swirl again, rinse, swirl again, do it at least 3 times to get it all out and get as much of that substance out as you can. Now you've got to make sure that you don't go above the line on the volumetric flask though, so keep an eye on that all the time. Then swirl it, don't invert the solution or anything like that, just swirl it, just so you can get it into the solution. Now what we need to do is pour water with a washing bottle into the neck of the volumetric flask until the line comes up to the mark that's etched on the bottle. And you can see that in the diagram that's on the screen there, that line around the middle, midway up the neck. Allow any air to run through the funnel. Carefully pour it until it's just there. Take the funnel away, rinse it out. Then use a little dropping pipette like that one in the picture and just drop it in drop by drop until you get the bottom of the curved meniscus sitting on that line. Stop with the volumetric flask and then invert it and basically do this sort of action, roll it around. If you don't do that, you're not going to mix it. And what we've had people do is titrations in the past where they take an aliquot with a pipette from the top of the solution and the middle of the solution and the bottom of the solution, and every time they do it, the concentration is different because they simply forgot to invert it. And then label it, and you should be ready to go. So basically, that's how you prepare a standard solution.